No, of a sufficient statistic. I've claimed that. See, I haven't proved that, right? And so if you accept that, then you have to say, well, what can I do with it? And what I can do with it is, if it's really true that this guy is a controlled Markov chain, then I can do this translation, and I've got all these tools available, Right? So that's the genius, really. The fact that you can actually show that. So the next steps. One is to convince you that this is a controlled Markov chain. 2, can we ever solve it? Is there a condition V3 or comparison theorem to get performance bounds? Can we use any of our machinery from before? Policy iteration, can we do it? And the answer is no to some of this stuff. Like, can we solve it? Generally, no way. Typically, no. Performance bounds, yes, because the comparison theorem, for example, doesn't require any assumptions at all. I mean, there's nothing, you don't need irreducibility or anything like that to get performance bounds. So this, yes, you can use that machinery, but a lot of stuff, no. But, there are examples, LQG, big happy face there, and bandits, yes. I mentioned applications to advertising and so forth. You don't go through this in detail, but you get so much insight from this that you get solutions that really work, and you can prove that they work. And so, I'm going to do this now, and we'll very briefly talk about this, and maybe a little less briefly talk about this after spring break. Okay? Yeah.
Typically known there?
What's that?
When you say typically known for any solver, like when for policy iteration or something?
Well, you can imagine, right there's the reason why. I mean, brave people do take the simplex and then create a grid to get a finite state space and then use policy iteration or something. I think one of you did that once. Didn't you do that? Yeah. In 2017, there was a problem where somebody actually did that. So that's one problem. One problem is the fact that the state space is no longer finite. In fact, it's continuous. Another thing is we're going to find out is that all of the Markov machinery that I taught you guys in the first month of the course falls apart. And the reason is, it's not because it's a Euclidean space for the state space. It's the fact that the noise is so discrete, that given the previous belief state and given my action, there's only like, say, 5 possible values of Bn, because of the fact that the y's take on a finite number of values, when you have a discrete observation space. And so there's this degeneracy that makes analysis really, really hard,
Can you do the transition with regards to the belief state, right?
Yeah, well, I'm about to write that down. Okay. Yeah. And I've got some notes here. I don't like them when I get to this part. It's these, the note, I'm not going to go through all these notes now because they're way more complex than they need to be. Yes, but I'll give you the main ideas. Yep.
You're saying yes for 2 and yes for performance bounds?
So yeah, check mark here, a little happy face. I'm not saying that it's used much, but you can. So if you have a problem with some structure, you can finally up enough functions, and they will give you performance bounds for sure. In case of bandits, you can't. LQG, you can solve it exactly. You can just go through. Everything works perfectly, because you get this. Because all the conditional distributions are Gaussian, so you're in a finite dimensional family. Yeah. So it's so this LQG turns out to be pretty trivial, and there's some beautiful structure that comes out. Again, all done in Florida. It's amazing. All Rudy Kalman's work here in the 60s. But again, in bandits, they don't go through all this stuff. They look at heuristics inspired by this, and then they show it works. Yeah. And I'll explain that. Okay. Yeah. Any other questions? You got the roadmap. So how do I don't want to go through this, but let me. So many of you have seen this before, haven't you? So many of you have seen the derivation of the nonlinear filter? No, I don't know. Yeah. Yeah.
So I guess when we started, we defined the cost to go. So if we were to redefine it for this problem, condition on the past data, we get something that doesn't grow.
Yes.
That was the idea?
That's the idea.
Okay. So then you recondition on script yn, you'll just get back something bn x.
Well, yeah, you can see right here. I've got it. I haven't proved it yet, but I'm claiming that the conditional distribution evolves as a controlled Markov chain, and then my criterion here can be written as a function of that controlled Markov chain. And so I'll just jump ahead, the very last line of these notes. So, so I can solve this with value iteration. Basically, this problem is something that we solved. Or at least, I gave you the solution for Markov chains in a finite state space. And the same formula goes as follows. You basically, V0 is given. I'm calling it the terminal cost here, but you can think of it as an initial condition in value iteration. And then you define Vn of B to be the minimum of all u of the cost now, my curly Q cost. Oh. I'll use the same kind of crazy notation I've used before. I'm going to call this BK plus 1. This looks jarring to me, but remember, I'm going to prove to you that there's a transition matrix. Right, and it's time homogeneous. So that K there is just a joke. I'm just saying, if my belief state is B and I put an input U, what's the conditional expectation of the of Vn plus of the last value function at that new belief state, one step in the future. All right. This was the value iteration algorithm I gave you before. You know, it really is. I mean, it's just that now you have to forget that BK has a meaning. It's just a Markov chain, and it happens to evolve in a simplex, you know? And so this conditional expectation can be computed for every B and every U. And you can run this value iteration algorithm. And again, the trouble is data storage, because, you know, B takes on any values in the simplex. Yeah. But what's that? Yeah. Yeah. Why not jump? Yeah. Why not say a few more things? So, what if let's just look at it. Let's look at V1. What's that? Oh, this is for this right there. So right now I want to. Oh yeah, that's right. So I mean, this is a now a function. This is my Vn, which is a function of B, B0. You know, I completely put this down in the standard MDP world now. You know, so my and there's a star here. I forgot the stars. You know, what's that? Yeah, I need stars. This is the optimal guys. Yeah, yeah. Right. I mean, is that clear or not?
Yeah, little n isn't the capital. Little n capital.
No. This is how you would. So capital N is my horizon. If I went to compute it, I'd do it through iteration. You know. So basically, we did say this. Both for the uncontrolled and the controlled case, that when you perform value iteration, you solve this problem for every n. Okay, so this function solves this problem with capital N replaced by little n, and you just keep doing this until little n gets capital N, and then you're done. Okay, okay, but yeah, let's do an experiment. So V0, V0 we already said was linear in Bn. Okay, that was my definition of script V0 of B. It was just a dot product. Okay, this is super abstract now, because before it was a Bn and I was really emphasizing as a conditional expectation, but I'm throwing all that away. You know, so if given any B, I've got a dot product, and B might not be, you know, it might just be something out of the simplex I pulled out at random, because after all, I can perform this iteration, and I'm trying to get a function for every B, you know, every possible B. What about V1? Is V1 linear? Check this out. With you know, so basically take n equals 1 here. You know, I mean, let's, you know, write it down again. So I've got some junk here. So I've got this guy here. Should we expand it out maybe? And then I've got this crazy thing over here. So this guy here, now I'm saying that n equals 1, so that's 0, so that's that linear function. Okay, so this is a linear function of b. It's just a dot product. And I'm asking you, what about v1? What kind of function is that? Let's see. Where is it? No, I did jump too far ahead. Let's stare at this a second. Everybody look at that for a bit. Huh.
What are we working towards?
Oh, it's some structure. So basically, I'm jumping to the end because of some questions. You know, no, what are we working? No, you tell me. What are we working towards?
I have no idea.
Oh, you don't?
No.
Well, let's go back to the beginning. So when you have a control problem, you have partial observations. We'd like to be able to use the machinery we developed for fully observed Markov chains. And we're getting there because some things I've shown to you that I can translate the cost to cost on this belief state. And that I haven't shown you yet that it evolves as a controlled Markov chain, but I'll show you that in a second. And then there are questions about computation. What do you do with this? So once I show you that Bn is a controlled Markov chain, what would you do with it? And is there any structure? And I'm getting slightly tongue-tied here because sometimes it's dangerous to ad-lib. Because it's not obvious to me now. For a fixed U, let me see, 1 second. I'm going to tell you something interesting. I want to tell you some structure. So again, V0 is linear. What about V1? Is there any structure? And can I show you any structure? 1 second. Damn. Okay, we're not ready yet. I see. I see.
With the min there, it is not linear, right?
What's that?
With the min there,
It's not linear, so no. You can see that from the first term, you know. Imagine if V0 was 0. You'd have just this initial term here. And so you'd have a minimum over U. It's not linear. So what is it? Suppose this wasn't here. How about V0 equals 0? What kind of function is that? Is a function of B. Just forget, let's make it easier myself. Take V0 equals 0. What is it? Not convex, it's a minimum, but you're close. So it's a minimum of linear functions. So for each U, that's a linear function. A minimum is concave. So it's concave. That's not relevant. It's without this, it's really clear. It's concave because it's a minimum of linear functions, and it's also piecewise linear because it's a finite number of U's. Okay. But. All right, so that's something you can show. So it's easy to see if V0 equals 0. It's even true without V0 equals 0. And that you can't tell until you see the transition matrix. That's why I jumped ahead too fast. But that's really cool because, you know, we're not looking, if we're trying to solve this problem, we're not searching over all possible functions on this region. We're just looking for functions that look like, like upside down bowls. So it's a very, very small class of functions, So it invites approximation methods. So you can imagine, you can basically say, well, I'm just going to look at quadratic approximations, and then try to get the best fit within quadratic functions, something like that, all right? You could, because, really, we are just now looking at an optimal control problem where the state space is just this little polyhedron, and we know we've got this nice concave function. That should be easy to approximate. So maybe these pound MDPs are really no harder than fully observed. Maybe you could, given this incredible structure. I know piecewise linear doesn't sound very quadratic, but screw that. We're going to be looking at large n. It'll be a very complex piecewise linear concave function, and a quadratic approximation might be fine, something like that. So we'll come to that. All right. Okay. So what to do? Let's take a break for 5 minutes. I need some water. Just